Am I audible to everyone?
Yes, madam. Audible.
Yes. Yes, sir. Okay, so in the last class we discussed about atomic models and then properties of cathode ray and then properties of anode ray. Hope you remember, right? Is there any new students in the class? Hope everyone are in the last class. Am I right?
Why don't you react, students?
I didn't attend last class.
Okay, fine.
No, if you
So
don't
what?
attend, you go through the video. That is the must. அது எப்படி உங்களுக்கு அது வராம போகுதுன்னு தெரியல. See, எனக்கெல்லாம் நாங்கெல்லாம் குழந்தையா இருக்கும்போது ஒரு கிளாஸ் நாங்க ஒரு ஸ்கூல் போலன்னா அடுத்த கிளாஸ் போய் என்ன நடந்ததுன்னு கேட்போம். அப்புறம் அந்த பாடத்தை வீட்டில் படிக்க ட்ரை பண்ணுவோம். So here you have a video. You should have gone through it. But somehow I'm not able to understand the current youngsters mentality. These are something for a reasonably good student will do that. So you do it, Tejaswini, from next time. If you can't come, it's fine. But it's there in our YouTube. You can go through it. At least in the chapter, book padikalam. I'm not saying you should go through the entire video, but you come to know that this is the chapter, atomic structure or something, and then you go through that in the book. That's very important. இல்லைன்னா அடுத்த கிளாஸ் உங்களுக்கு புரியாது. இன்னைக்கு வரும்போது உங்களுக்கு புரியாம போறதுக்கு ரொம்ப சான்சஸ் ஆர் மோர். ஸோ இது ஏன் இந்த பேசிக் ஃபண்டமெண்டல் ஏன் உங்களுக்கு தெரிய மாட்டேங்குதுன்னு எனக்கு தெரியல. இதெல்லாம் உங்க வீட்டில் சொல்லிக் கொடுக்கலையா, உங்க டீச்சர் சொல்லிக் கொடுக்கலையான்னு எனக்கு ரொம்ப சந்தேகமா இருக்கு. கேரியான் மேடம், சாரி.
எஸ். ஓகே. ஸோ
நான் வீடியோ இப்போ பார்த்துட்டேன் சார். இப்போ காலையில பார்த்துருக்கேன்.
ஓகே
ஓகே, குட்.
ஓகே ஓகே, குட் குட்.
Thank you.
Good, Tejaswini. If you have seen it, very good, very good.
Yes. So last class we discussed about the properties of cathode ray, properties of anode ray, and then how the neutrons is discovered, then about the Bohr's model, Rutherford model. So in today's class we have to start with the Bohr model. Before that we have few terms. We will discuss all the terms. Then we'll come to the Bohr's model, students. Okay. So just we'll see what we discussed in the last class. Just a glimpse of it. Okay. About the properties of cathode ray. What is a cathode ray? What does it mean, the cathode ray means? Yes, any of you who knows cathode ray? Nobody? Okay, see, cathode rays are negatively charged particles. Correct. So who found the cathode ray? J.J. Thomson. By the cathode ray evacuated glass tube he took. From that the rays are traveling from the cathode to anode. So he named as a cathode ray. Cathode ray is actually in what charge? Is it in positive electrode or negative electrode? Cathode.
It's negative electron.
Very good. It's a negative electrode. So definitely there is some rays are coming from the cathode which must be a negative. These are all some conclusions he did, and then it has a mass particle and some rays are coming which is traveling in a straight line. If you keep any magnets or some electrodes, there is a deflection which proves that the rays are charged particle. So we have seen some results from that experiments in the last class. So the main results are the cathode ray is a negatively charged particle. It will move in a straight line without any presence of electrical and magnetic field. If you place any electrical and magnetic field, it will deflect. Then one more important point, cathode ray is not depends upon the gas we are taken inside the chamber. Like the glass chamber we have to take, no? Inside the glass chamber we have passed the hydrogen gas. But the electrodes, the cathode rays is not depends upon the gas taken, or it is not depends upon the electrode. This is very, very important point. But when it comes to the anode ray is depends upon the gas taken, because the proton will vary from gas to gas. For example, how the anode ray is happening means, like you took hydrogen gas. Okay, hydrogen gas is passed inside a glass chamber and we are passing the electricity. So if you did electricity, what will happen? This will split into H plus ion and then electron minus. What is your H plus ion? This is your protons. Okay, this is only involving in the anode ray experiments. For example, if you take a lithium, so lithium I am passing electricity. So it may be in the gaseous form we have to send. Okay, lithium we are passing an electricity. it becomes a lithium plus ion and then electron. So the lithium plus is your protons. Am I correct? Now this is our positively charged particle. So the positively charged particle is completely depends upon what gas you are taking. Okay, what gas is passed inside the glass chamber. But what about the electrons? The electrons will not vary. Correct. The electrons is a fundamental particle present in all the elements. So it will not vary. So the cathode ray is not depends upon the gas we are taken, or it is not depend upon even the electrode. But in the case of an anode ray experiments, the anode ray is not coming from the anode first of all. So where the anode rays comes from? The anode comes from the anode rays are comes from the gases. Okay, so the anode ray is depends upon completely what gas we are taken. It's a very important point. Okay, who found the proton, students? That is an anode ray. Anode ray is also called as a proton. Who found the proton? What's the scientist's name? Goldstone, right? Goldstone only found the protons. J.J. Thomson found the electron. What about the neutron? Who discovered the neutron?
James Chadwick.
Chadwick. Very good. Chadwick discovered the neutron. Yes. The next point about, let's come to atomic model. How many atomic models totally we have? Yeah, first one is Thomson. Second one is J.J. Thomson. Second one is Rutherford model. And the third one is Bohr model. And the fourth one is quantum mechanical model. Right. So in the last class, we did J.J. Thomson model and Rutherford model. Simply, what is a J.J. Thomson model? Any one of you? What is it about? It is a very simple explanation for the J.J. Thomson model. He compared with a fruit. What fruit it is?
Watermelon, ma'am.
Very good. It's a watermelon. Exactly right. So in the watermelon, the electrons are simply scattered here and there. Then the protons are present everywhere, like the seeds. So in the watermelon, he considered seeds as an electron, and then the red color fruit part he considered as a proton. But it is a failure model. It's not correct. We know the exact structure now, but that time it was a failure model. Why the J.J. Thomson model is failure means he couldn't explain about the stability of atom. Okay, he is not explaining about the stability of atom, and then neutron. He didn't talk about neutron. So there are some failure model. So we are moving with the Rutherford model. So in the Rutherford model, there are many good results. So what he did, he is passing an alpha particle. What is your alpha particle? Helium positive. He is passing an alpha particle into an gold foil so that many of the alpha rays are moving in a straight line, which confirms that there are many empty spaces and very few alpha particles got deflected, so that the nucleus is in the center, and that too in a very, very, very small region when compared to the size of an atom. Am I right? Okay, that is a result he did. So this is an atom and this is a nucleus. So there are many empty spaces, so that the alpha particles are moving in a straight line. So when the alpha particle comes close to the nucleus, it got slightly deflected. The reason, the alpha particle is also a positively charged, which is an helium plus ion, right? Which is an helium 2 plus. This is also positively charged particle, and the nucleus is also a positive field, right? So when the helium comes near to the nucleus, it got deflected. And the third, so that he states that the nucleus in the center, and that too very, very small region when compared to the size of atom. Then the third ray is coming, which is exactly meeting the nucleus and got deflected at an angle of 180 degree. Okay, so it's got deflected at an angle of 180 degree. Exactly, it is going and coming back. It bounced back. It is because the nucleus is in the center. Again, it proves that nucleus in the center. So everything is correct in the Rutherford model. Then why the Rutherford model is failure? What is the reason? Why it is failure? Everything is correct. Why it is failure then? Yeah, because what he said, he didn't explain about the Maxwell concept. So the Maxwell concept is, if any electrons revolving in the orbit, okay, so we have an electrons here, the electrons are keep on revolving. So if keep on revolving, it will release some energy. If electrons, the electrons we know it's a negatively charged particle, any charged particle under acceleration, it will release some energy. Finally it will comes into the nucleus. Is this possible? Is this will happen in the atom? Definitely not. Yes. So if electrons falls into the nucleus means definitely, which proves that the molecule is or the atom is unstable. So this is Rutherford also failed to explain the stability of atom. His concept is the electrons are revolving. Where the electron is revolving and how it happens, he didn't explain. The electrons are revolving, and finally, like according to the Maxwell, if any negatively charged particle under acceleration, it will release some energy. If it releases some energy, then the orbit will shrink, then electron will comes into the nucleus. It proves that it is unstable. So he didn't explain about that, and he didn't explain about the line spectra of hydrogen. All those things we will see in detail. Okay. So before that, next one is our Bohr's model. Am I right? Right. The next one is Bohr model. Okay. Before moving into the Bohr model, so limitation of Rutherford we have discussed. Let's come to Planck's quantum theory. Okay. What is in Planck's quantum theory? What is the use of Planck's quantum theory? What's the main application? See, these Planck's quantum theory is actually an which proves the electron is particle in nature. Okay. See, actually, electron has a dual character. One is a particle character. The other one is, what is the other character? Particle character. Another one is wave character. Okay. The Planck's quantum theory is explain about the electron is having a particle character. He did some experiment. Based on the experiment, he is proving that electron is having a particle character. But we know electron is a particle already, because in the cathode ray tube experiment, he is placing a small fan and the invisible rays are coming. While the rays are coming means the fan starts to rotate, which means the electron is some masses. Any substance has some masses means definitely it must be a particle. We know it's a particle, but based on some experiment, let's see how the Planck's proves the electron is having a wave particles. Sorry, particle nature. So, you know the quanta. What does mean by quanta? Before that, we have to know quanta. Quanta. Any idea about the quanta?
Is it big?
Sorry.
Meaning is big? Big.
Big.
I don't know.
No. Yes. Okay. So it's actually small packets of energy. Okay. What is it? Small packets of energy. This is what mean by quanta. Small packets of energy. So if the small, see, energy may be in a different form. Okay. If energy in the light form means, then we can say the quanta as a photons. Okay. The photons are the small packets of lights. What is mean by photons? This is a small packets of light. Okay, there are many types of energies. You know the light energy, photo energy, thermal energy. There are many form of energy. So energies are traveled in the small packets. Actually, the energies are traveled in the small packets. All the small packets are called as a quanta. Okay, it's called as quanta. Then if the energy is light means, then the small packets of light is called as photon. PHOTON. It is called as a photon. So based on this photon experiments, he is going to explain the particle nature of electrons. Let's see. The energy associated. So we know the formula. Energy is directly proportional to, what is this? Nu, right? It is nu. Energy is directly proportional to nu. Here it denotes frequency. Nu is nothing but frequency. Three things we have to know very careful when it comes to frequency, lambda, and then wave number. What is all those things? Wavelength is mentioned as lambda, frequency is your nu, and then wave number is your nu bar. What all those things? See, For example, let's consider this is an x-axis. The waves are moving like this. Okay. What is this position called as, students? Any idea? What is this position called as in waves?
Crest.
Very
A
good.
crest.
Yeah, very good. This is crest. What is this position called as?
Trough, ma'am.
Very good. It is trough, right? So it is trough. Okay. Then I think hope you know what is a meaning of wavelength. What is a wavelength then?
Yes, ma'am. A distance between one crest and another crest, or one trough and another trough, is wavelength.
Very good. So the distance between the two crest or the two trough is known as the wavelength. It's a lambda. Okay, mostly wavelength is mentioned in the nanometer. The unit is meter, either meter, nanometer, angstrom, whatever we can take. Wavelength, it's a lambda, which is nothing but the distance between the two adjacent crest or the two trough. This is what known as lambda wavelength. Then what about the frequencies? Frequency means, yeah, frequency in the sense this is a number of waves passed in 1 second. Number of waves passed in 1 second. Okay, this is our nu. So what is the symbol of nu? Hertz unit. I'm asking the unit. Hertz, H is at mostly represented. Then what is the wave number? Very similar to the wave nu. Number of waves passed in one length. Okay, it is like 1 meter or like that. 1 meter. In one length means we can say as a nu bar. So lambda is the distance between the two crest, adjacent crest, or the two adjacent trough. The unit is meter, nanometer, angstrom, we can say anything. And what is a nu? Nu is nothing but number of waves passed in 1 second. For example, in 1 second, I have 20 waves means the 20 waves is your nu. And what is a nu number? Which is number of waves passed in 1 meter. That is your nu number. Okay, that is your nu number. Yes. So 1 meter, which is opposite of lambda actually. This is 1 by lambda. So that the unit is meter inverse. You can write as meter inverse. Then what does mean by amplitude? What's an amplitude, students? The height of the wave. Okay, this is what called as amplitude. This region is called as amplitude. Okay, this is your amplitude. Amplitude in the sense the height of the wave simply. Okay, so yes, let's come to the energy. Energy is directly proportional to nu. Nu is your frequency, right? So that means directly proportional, you know, one is increases, the other one will also increase. So always to remove the proportionality, we have to add some constant. What will be the constant can be used here? Yeah. What is the constant?
Planck constant.
Very good. It is Planck's constant. So E is equal to h nu. So h is a Planck's constant. What is the value of Planck's constant? All these constant values are very important, which is similar to our Avogadro number, right? Very important. 6.62 into 10 to the power of minus 34 joule second inverse. This is our Planck's constant. This is a very important formula. Energy is equal to h nu. This is very important formula. So we know that all the energies are traveled in a small packets called quanta. If the small packet, like if the energy in the form of a light, then what is it called as? If energy in the form of a light means, what is it small packets called as?
Photons.
Very good. Exactly right. It is photons. Yes. Any doubts? Okay. The small package is called as a photons. Very good. So energy is equal to, we can write NH nu. What is N denotes for? N denotes for number of photons. Okay. Here we are considering for the light energy. So the light energy is depends on the number of photons striking in an object. Okay. You have one substances. So here you have a substance. You want to find the energy. So the energy is the light energy, which is of photons. A small packets of light energy, which is of photons, striking in an object. For that, to find out the energy, E is equal to NH nu. N is nothing but number of photons. H is your Planck's constant. Nu is a frequency. Yes, this is again a very important formula. Okay. So the next one is about, there is a formula for nu, which is, what is the formula? Any guess? I think you people know already. Relation with the velocity of light. Nu is equal to in relation with velocity of light. What is the symbol for velocity of light? C. Right.
No, C by lambda.
Very good. It is C by lambda. Exactly right. It is C by lambda. So nu is equal to C by lambda means I can substitute the nu value over in the energy formula. So what's my new energy formula? It is E is equal to N H C by lambda. So this is our one more formula. If wavelength is given, then you can use this formula. Any doubt in this question, students? Are everyone clear?
Yes, ma'am.
Okay. So what
Yes,
is
ma'am.
the, very good. So what is the value of C, velocity of light, which is 3
3
into,
into 10 to the power 8.
3 into 10 to the
meters per
power
second.
8.
very good, 3 into 10 to the power of 8 m by s. Very good. Yes. Okay. So sometimes the unit conversions are a bit difficult when it comes to this chapter. So wherever you are getting a new values, just take it down in your note. Otherwise, keep one separate note for the formulas as well as your unit conversions. Here you are dealing with many unit conversions. So all the unit conversions are very important. The one important unit conversion is 1 electron volt is equal to 1.6 into 10 to the power of minus 19 joule. Sometimes one will be in the electron volt, the other one will be in the joules. So you have to use this formula. Unit conversion is very important in this lesson. Clear, students? Is there any doubt so far?
No, ma'am.
No.
Okay, fine. So we'll move to the next question. Question is, calculate the energy of 100 photons if lambda is 2000 angstrom. Okay, if the lambda is 2000 angstrom. So this is a question. So tell me what formula we have to apply. We know two formulas. One is equal to E is equal to NH nu. The other one is E is equal to NHC by lambda. So which is an apt formula for this question? So the given is N value. N value they given 100 photons. Then what is our lambda value? Lambda value is
2000.
very good. It's in 2000 angstrom. Okay. So which formula is apt? Whether energy is equal to NH nu or the
E
energy
equal to
E
NH
equals
by lambda.
NHC by lambda.
C by lambda.
very good. Energy is equal to NHC by lambda. So we know the value of N. N is 100. H. Here the problems comes because H is in the meter. H is not in the meter. The C is in the meter second, and H is in your what is the unit of the H? It is in joules second inverse. So for that we can apply the electron volt formula. So this also you can take it on. The value of Hc in electron volt is 1 to 400 and electron volt. Okay, electron volt angstrom. This is the Hc value. Take it down as the lambda here is in the angstrom. The value of Hc is 12,400 electron volt angstrom. This is our value. So we can just substitute the value directly 1 to 400 electron volt angstrom divided by how much wavelength is given? 2000 angstrom. So what's the answer? Will you people tell me? Angstrom get cancelled. What's the final answer? $620, right? So this is 620 electron volt. So for example, they are asking the energy in the joules. So how can we convert? They are asking the energy in the joules.
I'm multiplying by 1.6 into 10 to the power minus 19 joules.
Superb. So 1 electron volt is equal to 1.6 into 10 to the power of minus 19 joule. So that just simply multiplying into this into 10 to the power of like 1.6 into 10 to the power of minus 19, you will get the answer. That's all. Very simple. Okay, the final answer is you just do it. Let's move the other one. Clear, students? Is there any doubts? Hope
No,
it's
ma'am.
clear. Okay, yeah, fine. So next one, we'll move to the next concept. The next concept is photoelectric effect. So this photoelectric effect helps the electron is having a particle nature. All this experiment he is doing just to explain the electron has a particle nature. Photoelectric effect. So we can easily get the meaning from the name itself. What does it mean, photoelectric effect? Any idea? Photo means here it denotes photons. What does mean by photons? Photons are the light particles. The smallest packets of light particles are called as a photons. So during these photons, there will be some electricity. Here it is simply denotes electricity, but in some cases we use to represent as electrons. Anyway, both are same. So again, he did some a cathode ray kind of a tube experiment. So let's draw it. This is connected to the battery, two electrodes. Here we have one electrode, here we have other electrode. So I am connecting this to the negative terminal and this is our positive terminal. Okay, this is a negative terminal. Now tell me, what is this electrode charge? What is an electrode charge now? So the negative terminal is connected to the plate. That means this is our negative electrode. What is a negative electrode called as? Cathode, right? This is our cathode. Yes. The positive plate is connected to the other electrode, the positive terminal. So this is your positive electrode, which is called as anode. Okay, this
No.
is our anode. Yes, exactly right. So here we took some metal. No, that metal is actually an photosensitive metal. What does mean by photosensitive metal? Yeah,
Um,
yeah, yes.
it reacts
Ma'am,
with
that's
when
light.
there is light, ma'am.
Very good, superb. It will respond towards that light. Okay, it will do some changes when the light ray uh, hits to that metal. Very good. Yes. So this is a metal, photosensitive metal. Okay. So now what will happen? We are passing the light energies. So while we are passing the light energy, what will happen? The electron starts to eject. Okay, the electrons are starts to eject from that particular metal. That is what called as the photoelectric effect. So you are passing the photons. Photons is a small packets of energy. You are passing in photons to the plate so that the electron starts to eject from the surface of metal, and where the electron will move, where the electron will travel.
Towards the positive area, ma'am.
Yeah, very good. Towards a positive plate. So the other side we have an anode, which is an positive electrode. The electron will start to attract towards a positive electrode. Because of this reason, the current will be produced, so that it's called as the photocurrent. Okay, it's a photocurrent. You know, the electrons will travel in this side means the current will be of opposite direction. So now my electrons are coming like this. Okay, the electrons will move like this, electrons will travel like this. So what is the current charge? The current charge is like this. The current
Right.
charge is exactly opposite of the electrons arrow mark, right? So it is traveling in the opposite directions. Okay, this is what mean by photoelectric effect. So as because of the electron ejected from the photosensitive metal, okay, so the electrons are attracted towards the anode, so current is generated, that is called as the photocurrent. Are you people clear? Is there any doubts?
No, ma'am.
Okay,
Ma'am, which metal can be used as photosensitive metal, ma'am?
it may be of any metal, mostly lithium, sodium, potassium, and all used. It may be of any metals we can take. Only thing is we have to give the correct amount of energy, then only the metal will start to eject. All the metals are different. It's not like all the elements in the universe is not same. For example, sodium will eject an electron at 20 kilojoule, means maybe a magnesium will eject the electron at 40 kilojoule. So we have to, it's depend upon how much photons we are giving. We can take any photosensitive metal. Clear, ma?
Yes, ma'am.
Okay. So yes. So which proves that here the electrons are having a particle nature. Okay, it's an electrons are having a particle nature. Then the very important thing here, it's a threshold. Threshold frequency, threshold energy, all those terms are very, very important. Okay, this is actually a work function. Psi, which is work function. What does it mean is all the metal have a different work function. That is what I said. For example, it's just for an example, let's take an sodium metal. Okay, the sodium metal will start to eject an electron at 20 kilojoule. Then the 20 kilojoule is a work function of the sodium. So you have a magnesium. The magnesium metal will eject an electron at 40 kilojoule. Then the 40 kilojoule is your work function of the metal. Work function is simply minimum amount of energy required to eject electron from the surface. Okay, from the surface of metal. That is your threshold energy or threshold work, whatever we can say. This is a work function simply. So this is our minimum energy. Okay, it's a minimum energy required to eject electron, from the surface of metal. This is very important, from the surface of metal. So as we said, for example, we will fix it, the sodium metal will eject the electron at 20 kilojoule. You are giving 15 kilojoules of photons. Whether the sodium will eject electron now?
No, ma'am.
Of course not. Yes, because the 20, yeah, exactly right. Because the 20 kilojoule is needed. Am I right? The 20 kilojoule is needed. So that kilojoule is not enough to eject the electrons. Yes. Okay. For example, you are giving 40 kilojoules of photon. Okay. A photon having an energy 40 kilojoule. Whether the material will start to eject electron, the sodium,
Yes, ma'am.
Yes,
of
ma'am.
course, yes, of course. Because we have fixed for the sodium only 20 kilojoule. Only the 20 kilojoule is the minimum energy needed for the sodium to eject electron. And we are giving an 40 kilojoule, of course it will eject electron. Then where the remaining 20 kilojoule will go? Any idea? Any idea, students?
Ma'am, does sodium absorb those, ma'am?
Yeah, very good. The sodium, the remaining, it's not about the sodium, the ejected electron. No, the ejected electron will absorb the remaining energies that will be used for the kinetic energy. I'll explain those things. Okay. So what is our side? What is this? This is our
Work function.
this is our work function. We can say threshold frequency. We can say minimum energy is needed. Even we can compare with the minimum energy. So what is the formula for minimum energy? H energy formula is H nu. Okay, energy formula is H nu. Here I am comparing with H nu naught, which means that nu naught is your minimum frequency needed. Okay, minimum frequency is needed to eject electron. Minimum frequency is needed to eject electron. This is your H nu naught. Okay, minimum frequency is needed. Again, so instead of nu naught, if you want to replace, like what formula we can replace with the nu naught? Yes? What formula we can replace with the nu naught, students?
Ma'am, C by lambda.
Very good. So it is Hc by lambda naught. Again, I'm mentioning lambda naught. See, nu naught is my minimum frequency needed to eject electron means what is my lambda naught then? What is my lambda naught then? Again, I can say it's a minimum wavelength. Okay, it's a minimum wavelength needed to eject electron. Am I right or wrong? Shall we say like this?
Yes, ma'am.
So minimum wavelength needed to eject electron. All the terms are very important. See, like psi, which is a work function, minimum energy is required to eject an electron. nu naught, it's a minimum frequency required to eject electron, and lambda naught, minimum wavelength is needed to eject electron. All the minimum you can replace with a threshold. Okay, even you can say threshold frequency, threshold wavelength, threshold energy, which means that minimum energy is needed to remove an electron. That is what the threshold meaning here. Okay, so now we have found this formula. As I said, sodium needs of 20 kilojoules. You are supplying 40 kilojoules. Okay, and the remaining 20 kilojoules will be helpful for the kinetic energy of ejected electron. Okay, it's a kinetic energy of ejected electron. Now we have one more formula, which is EI is equal to work function plus kinetic energy. Okay, see, listen carefully. I already told you EI in the sense this is our energy of incident photon. Okay, this is our energy of incident photon. So now I am passing an incident photon having an energy of 40 kilojoules. Let's take a 40 kilojoule. And what is the work function of sodium metal? This is for just an example, students. It's not actually a 20 kilojoule. Just for example, I said here. So let's consider the work function of sodium metal. What is the work function of sodium metal? We fixed 20 kilojoules. Am I right? Yes or no? Yeah. So work function, let's take a 20 kilojoules. So the remaining will be your kinetic energy. Then again the X will be a kinetic energy. So listen, you have a metal here. You are passing the photons. What is this? This is your photons. You are passing a photon of 40 kilojoules. Okay. So this electron from the surface will start to eject, having an like to eject from the surface you have to take, for that process you need 20 kilojoules, right? The remaining 20 kilojoules used for the kinetic energy of electron. Okay, the remaining 20 kilojoules is used for the kinetic energy because the electrons has to move everywhere, no? So the remaining 20 kilojoules kinetic energy is your energy of movement, motion. So the 20 kilojoule is used for the kinetic energy of ejected electron. Is it clear so far? Is there any doubts?
No, ma'am.
Okay. Yeah. Now we can replace the formula of EI is equal to. So let's write the formula again. EI is equal to work function plus kinetic energy. So EI, let's mention as h nu. Okay. And what is a work function? In terms of h nu, will you people tell me what is a work function?
H mu naught, ma'am.
Very good. It is h nu naught. Exactly right. This is h nu naught plus kinetic energy. Again, this formula is most useful. Based on that, you will be having many problems. So h nu is equal to h nu naught plus kinetic energy. If they are asking in kinetic energy, then h nu minus h nu naught is equal to the kinetic energy. So these two formulas are very important. Clear? Yes, we will solve one more question based on this. See, during this process, like it is an it's an instant process actually. See, like at a time of maybe this photons eject this photon striking the metal surface, then the electrons will not take much time to eject from the surface. The same time, there is no time lag. Same time the electrons will eject from that particular surface. Okay, so it is a very spontaneous process. That for the ejection of electron, it will not take time. There is no time lag. Immediately the electron will comes out from the surface of metal. Okay, based on this formula we will solve one question. Write the question. Oh, no need. If the work function, the question is work function is given. Work function is given as 3.1 volt, 1 electron volt. Then threshold wavelength they are asking. Lambda naught they are asking. Threshold in the sense lambda naught they are asking. And they are asking kinetic energy too. They are asking kinetic energy also. The electron emitted of the radiation of 300 nanometer. Okay, like the electrons, the kinetic energy of the electron, lambda is given, okay, which is of 300 nanometer. So which formula we can use it? Will you people think a 2 minutes time? Yes, students. What formula we can use? There's two formulas we have to apply here.
Ma'am, for finding out the um, lambda naught, I think we can use work function equals h into c by lambda.
Okay, from that what you will find?
We'll find the lambda value, I think, ma'am.
Okay, we can find the lambda. Lambda naught is already given, no?
Lambda naught, I don't think it's lambda is given, lambda naught is not given, ma'am.
Okay, lambda naught. Very good. We can find the value of a lambda naught, right? Yes,
Yes.
exactly right. Okay. So the formula is from the work function. We know that work function is equal to h nu naught. So instead of nu naught, we can replace it with the c by lambda naught. So again, the work function is given as 3.1 electron volt. So it is 3.1 electron volt and Hc. What is our Hc value? I told you previously. What's the Hc value? It is
It's 1 to
1 to
400
yeah,
electron volt
angstrom,
angstrom.
right? But as it is given as a nanometer, okay, I can use 1240 electron volt nanometer. Okay, so now as because of the nanometer and angstrom, so I have put it's not 12,400, it is 1240. So this is our Hc value and lambda only we have to find out from this one. So if you found the value of lambda naught, okay, so I am finding the lambda naught which is equal to 1240 electron volt nanometer divided by 3.1 electron volt. So I'll be finding this. So based on that, kinetic energy is very easy to find out then, because we know kinetic energy is equal to H, what's the formula? H nu minus H nu naught, right? This is H nu minus H nu naught. So what is an H nu? Again, I can replace with Hc divided by lambda, and here also Hc divided by lambda naught. So what is Hc divided by lambda naught? Just substitute, you will get the answer. Okay, if you substitute, you will get the answer, final answer. Calculation will take time, so we'll move to the next one. Are you people clear in this question? Any doubts? See, first time finding the lambda naught by using the work function of metal. Then once the lambda naught you found, you can use the kinetic energy formula and substitute the kinetic energy, the h nu minus h nu naught. So the lambda naught value I am substituting here. So I'll find the kinetic energy. Is there any doubt, students? Because Hc is your how much? It is 1240 electron volt nanometer. What is your lambda given? The lambda is your 300 nanometer in the question, right? In the 300 nanometer minus what is your Hc? Again 1240 electron volt nanometer divided by what is your lambda naught? So lambda naught is your 1240 electron volt nanometer divided by 3.1 electron volt. So you will get the answer finally. Any doubt in this question? Clear? Everyone clear or not?
No,
Yes.
ma'am.
Yes, okay. So next very important one. It's very important. So nu. So what is a nu? In that photoelectric current? Nu in the sense what in the photoelectric current? In the photoelectric effect or photoelectric current, whatever it is, nu is nothing but the frequency of the light used, frequency of the photon simply. So you know that E is directly proportional to EI. EI in the sense The energy of a photon is directly proportional to the frequency of the light. So this is also directly proportional to the kinetic energy. Of course, it is sure because you are giving an 40 kilojoules, the 20 kilojoules is used up to remove an electron. The remaining 20 kilojoules is your kinetic energy of the electron. In case you are giving an 100 kilojoules of the ejected like energy of the incident, right? Only 20 kilojoules will be the ejected electron to remove an ejected electrons. Then remaining 80 will be used up for the kinetic energy. Am I right? So greater the energy of incidence, greater will be the kinetic energy. Clear everyone? Greater will be the kinetic energy. Is there any doubts? Greater the frequency, greater will be the energy of incidence, greater will be the kinetic energy of ejected electron. Here you can write kinetic energy of ejected electron. Okay, next let's come to intensity. Always we used to get confused between the intensity and energy. Intensity is actually depends upon number of photons. Okay, what does an intensity means? Intensity is directly proportional to number of photons. Okay, intensity is directly proportional to number of photons. More the number of photons, more will be the electrons ejected. This is also directly proportional to number of electrons ejected. Remember, this is a very important thing. One photon will eject only one electron. Okay, one photon will eject only one electron. So more the number of photon, more will be the electrons ejected. Clear, students? More the number of electrons ejected, then definitely the current will also be extremely greater. This is an important point. Is there any doubt so far?
No, ma'am.
Okay, fine. Yes. Next one, let's come to the Bohr model. Okay, based on this, the scientists confirmed that the particle nature, Max Planck, so considered the electron is having a particle nature. Because of the particle nature, so as we are giving an energy, it comes out. So of course, it has some particle nature. Now let's come to the Bohr model. Okay, Bohr's model. So what's the main application of the Bohr's model? So we know the Rutherford, the main limitation in the Rutherford model is discussed is like the electrons are keep on revolving in the orbit. Any negatively charged particle or any charged particle under acceleration, it will releases some energy so that the electron will finally comes into the nucleus. So the atom is unstable. But Bohr, what the Bohr is saying, of course the electrons are revolving. There is no doubt the electrons are revolving in the orbit. But the electrons are revolving in the fixed orbit. There is no energy release. Okay. Here the energy is not released because the electrons are revolving in the fixed orbit. The word only the Rutherford mixed is Rutherford has didn't explain is fixed orbit. Okay, the fixed orbit is very important. So Bohr, according to the Bohr concept, the electrons are revolving and the electrons are revolving in the fixed orbit so that there is no energy gain or energy loss. This is what the concept. Then mainly he took for one electron cases, like one electron cases in the sense he explained the all the atoms or the ions with only one electrons. So one electron means what we can take hydrogen. Hydrogen is an one electron species, right? It has an one electron. He discovered for electron also. He explained for electron also, but electron also for helium also he did for helium plus, not for a neutral atom. Okay, what is the atomic number of helium?
2, ma'am.
Very good. Then what is an helium plus? How many electrons are present in helium plus?
That will be only 1 because
Yeah,
one
very
electron.
good. Yes. So for example, lithium. Lithium has a charge of 2 plus. Again, if you take a lithium has 3 electrons, but the lithium 2 plus has only 1 electron. So Bohr's model is applicable only for the single electron species like hydrogen, helium plus, lithium 2 plus, all those things. Clear, students? Is there any doubts?
No, ma'am.
Okay, so the very important thing, electrons revolving in fixed orbit. Okay, electrons are revolving in fixed orbit. This is a main concept that only Rutherford is forgot to say that, or he missed to say that, revolving in fixed orbit. This is very important point. Okay, in a fixed orbit. Then, what is the formula for momentum? Definitely, you people have learned, I think, in physics. Momentum. What's a linear momentum, or else? Yes. What's a linear momentum? What's a momentum formula or the symbol of momentum?
It's the rate of change of acceleration, ma'am.
Okay, very good. Yes. So it's denoted as P, and then the formula is m into V. Hope you remember. This is for the linear momentum. Correct? This is for the linear momentum. Mass into velocity is a linear momentum formula. So here we will be discussing for the angular momentum. For the angular momentum, the formula is mv into r. Here r denotes for radius. So why we are discussing the angular momentum is, see, there are many. We are like, what we thought is hydrogen. Hydrogen has only one electron. So the electrons will be present in the first orbit. Correct? But the hydrogen has many orbits. It has an infinite orbit. So in that, electron will present only in the first orbit according to our Aufbau's principle. Because Aufbau principle is saying, according to the energy level, we have to fix the electrons. The first shell has the lowest energy, the electrons in the first energy. But you have a many orbits, infinite orbits. But as there is only one electron, it is placed in the first orbit. So what the one more point Bohr is saying is, so the electrons are the many orbits in the all the atom, but the electrons will place only at the integral multiple of h by 2 pi. What is an integral multiple? What's an integral multiple? He is relating mvr is equal to h by 2 pi. So integral multiple in the sense just simply multiplying with n. So n maybe you are 1, 2, 3, 4. All these are the n values. N is equal to 1, 2, 3, 4. So the electrons will sit only in the integral multiple of orbits. Okay, in the integral multiple of angular momentum. That is what he is saying. It will not go and sit simply where it likes. It's based on the energy level, as well as if the orbit possesses h by 2 pi, integral multiple of h by 2 pi, then the electrons will sit in that place. That is what this concept about mvr is equal to nh2 pi. So that what we can say, the orbit is quantized. What does the word quantized mean?
It can be only in a certain number, ma'am.
Yeah, very good. It is fixed. We can say some fixed values. Quantized in the sense fixed values. For example, if you take the first orbit, so here you have a nucleus. This is a first orbit, second orbit, third orbit, fourth orbit. The first orbit is actually 1h2 pi. Okay, and what about the second orbit? The second orbit is actually 2h2 pi. So that's what the integral multiple, 2h2 pi. So based on that only the electrons will sit. And all these orbits are stationary. That is, it will not come and fall into the nucleus. That is a very important point. The both discussed in this model. Yeah. Next, let's come to energies. So whether the electron is having some energies or not?
Yes, ma'am.
Of course, the electron is having energy. For example, let's say this is a nucleus. This is the first orbit. This is the first orbit. And this is the second orbit. And this is our third orbit. Okay. Let's take a hydrogen itself. Okay. We have an hydrogen atom. One electron species. You have an one electron here. So the hydrogen, the first electron has to move into the third orbit. What it will do? The first electron in the orbit has to move into the third electron. So whether we have to supply energy or we have to release energy for this, what the atom will do, whether it will absorb the energy or it will release as energy.
Ma'am, it wants to observe energy.
Very good. It has to absorb energy. Very important. Now the electrons in the first orbit, in order to go to the higher energy state, it has to absorb energy. Again, from the higher energy state, it has to comes to the ground state. What it will do? It will releases that energy. Am I correct? How much energy is absorbed for first to third, it will release us from third to one again. This is very very important. So from ground state to the excited state, it will absorb energy. Okay, it will absorb energy from excited state, excited to the ground state. From the excited to the ground state, it will releases that energy. This is an important point. Releases energy. What is a what's a relation between energy and stability?
Higher the energy, lower the stability, ma'am.
Very good. Energy is inversely proportional to a stability. Whether the electron will be more stable in the excited state, is it will be
No,
more
ma'am.
stable? No.
It will be
So
stable in the ground state, ma'am.
very good. It will be stable in the ground state for a very, very, very less time. It will be resides in the uh, excited state. Okay, the energy will be lower means more will be the stability. So the electrons will prefer in the ground state than in the excited state. Even if it goes to the excited state, it will stay there only for a very, 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 very less time. Okay, it will comes to the lower energy state. So I think remaining we will discuss in our next class in detail. Is there any doubts so far, students? Are you people clear till now?
Yes, ma'am.
Okay, fine.
Yes, ma'am.
Yes, okay, good. Shall I ask you few questions?
Yes, ma'am.
Yes, ma'am.
Okay, okay. So, what does it mean? H nu naught. What does H nu naught means?
Ma'am, H mu naught is the
Ma'am, it's
work
minimum
function, ma'am.
frequency to eject electron.
Yes. One more answer.
Work function, ma'am.
Yeah, it's a work function. See, I am saying nu naught. Simply a nu naught means which denotes the frequency of the threshold frequency or minimum frequency needed to eject an electron. What is mean by H nu naught, which is your energy. So it's a minimum energy required to eject an electron. Either you can say work function or the energy of electron. Clear, ma?
Yes, ma'am.
Okay, fine. Yes. So we will see in the next class. Thank you.
Thank you, ma'am.
Thank you, ma'am.
Yeah, ma. Sir, are you here, sir? Okay.
டீச்சர் என்ன சொன்னாங்க, 3 டீச்சர்